Okay, hello and welcome, and thanks to all of you for joining us for the first in the series of Red List webinars. These webinars are aimed at the members of the IUCN Species Survival Commission, and please note that we're also recording these webinars as well, so we're going to make them available probably through the Red List website. I'm Caroline Pollock. I'm the Senior Programme Coordinator for the IUCN Red List Unit based in Cambridge in the UK, and I've worked with the Red List Unit staff on all sorts of issues around managing the IUCN Red List of threatened species and providing support to all of the assessors that contribute to the Red List. So part of our role is obviously providing advice and guidance, and we're very aware that all of you invest a lot of time and energy on doing Red List assessments, and we thank you very much for that. We also know from when we do a Red List update that there are clearly some areas that people have problems with. They struggle to get right or to understand fully what the process is. So the whole purpose of these webinars is to basically provide some practical guidance and advice to all of you who are doing assessments and providing your time and knowledge to the Red List. So in this first webinar, we are going to focus on the Red List criteria. And we've chosen 4 main topics to cover really, but we're not going to be restricted to that. During the registration process, we actually asked you to provide some comments and questions of your own to highlight areas that you want to hear about. So we will try and answer your questions as we go along through this webinar. We only have 90 minutes, so please understand that we might not be able to answer absolutely everything. So if there are any questions that we don't manage to answer in this session, we will either follow up by email or we might have to hold topics back for a future webinar. So do bear with us, we'll do the best we can. Throughout the webinar, you are welcome to post additional questions on the topics that are being covered. Please can you use the Q&A function on Zoom. You'll find a Q&A icon right at the bottom of your screen. Use that to post your questions and we'll do the best to answer them. We have Clay Meredith, Tim Lyons and Anna Walker from Albuquerque Biopark to help us answer your questions and to point you in the right direction. So I'm delighted to welcome our speaker for today, Professor Resit Akçakaya, who is the chair of the IUCN SSC Standards and Petitions Committee. And Resit was also one of the main people involved in developing the quantitative criteria we use on the Red List, and is central to keeping the guidelines updated and relevant. So welcome to Resit, and I'm going to hand over to you now to carry on with the rest of the webinar. Thank you.
Thank you, thank you, Caroline. And hi, everyone. Thank you for attending this webinar. I'm Resit Akçakaya. As Caroline said, I am the chair of the SSC Standards and Petitions Committee. Our function is to develop the guidelines that Red List assessors use in assessments, and also make rulings on petitions of Red List assessments. I am also, well, my day job is a professor at Stony Brook University, which is part of New York State, the State University System of New York. I am in the Department of Ecology and Evolution. I am an ecologist by training. My research has focused on extinction risk assessment, and more recently I have been working with the green status criteria and developing the green status of species. So let me share my screen. Okay. Can you see my screen now?
Yes, we can.
Okay, great. So in this webinar, I'm going to cover a number of topics. Number of questions that you asked, I selected some of them and I changed them. So the questions that I'll be displaying and talking about are kind of loosely based on your questions. And then I'll also talk about some difficult quantities that we need for Red List assessments, including severe fragmentation, generation length, and reductions. As your invitation indicated, this seminar is on these more difficult concepts. It's not an introductory seminar, so I am assuming that you are all familiar with the Red List guidelines, and you have taken the Red List online training course. So as I said, this is not an introduction to Red List, but we do need to talk about a few fundamental concepts that underlie the Red List criteria. And one of them, of course, is the purpose of Red List. Why do we do Red List assessments? Now, you all know this, but still, I think it's worth emphasizing. The purpose of Red List is to classify species according to their extinction risk. And extinction risk means the likelihood that the last individual of the species will die in the near future. And specifically, the purpose of the Red List is not to list rare species or depleted species or declining species or species that need protection. It's not for mapping to be used for conservation, and it's not for determining conservation priorities. Now, of course, we do use Red List results to determine conservation priorities, but as the Red List criteria say on the first page, while the Red List focus attention to the taxa that are at the highest risk of extinction, it's not the sole means of setting priorities. And that's important to remember because a number of misunderstandings about the Red List, I think, result from not paying as much attention to the underlying purpose. So with that said, let's start with a few of your questions. As I said, these are kind of loosely based on your questions, not exactly what was asked. So here's a question. This is similar to many questions that I have gotten over the years that I was chair of the Standards and Petitions Committee. It says, based on the available data, a species is assessed as least concern. But we know that there's overexploitation, illegal hunting, and/or trade. How can we assess such a species more accurately in order to save it? So first, focus on the more accurately part. Now, if the data are sufficient and the criteria are applied correctly, and the result is least concern, then least concern is the accurate category. There is no way to make it more accurate. Of course, this is easier said than done, and there are many cases where we know there is overexploitation. There is some fragmentary data. We don't actually know exactly how to use it. And I'll come to that in the section in which I talk about reductions and declines. But the important thing is that if you use the data that is available correctly, then the effects of these threats should already be incorporated. Now, I'll talk a bit more about threats in the next slide, but the point is that the focus of the criteria is looking at the data and determining the status of the species based on the data. Now, let's focus on this last bit in order to save the species. Yes, of course, our ultimate goal is to save species, but the only way Red List can do that or can contribute to that process is if it is credible, if it's a credible way of assessing the extinction risk of species. And the credibility comes only from consistent and objective assessment of extinction risk. So that's the most important thing that we focus on, that the methods are applied in a standard way, consistently, so different taxonomic groups are comparable, and the assessments are objective. Now, I mentioned the information about threats. Now, this slide is a bit complicated, but basically what I am trying to say here is that there are a lot of different types of information we use in a red list assessment. And these can be roughly categorized into three groups. First, there are what I call symptoms. These are data on population size, population trends, range area, the trends in range area, fluctuations, fragmentation, all of those information about the species itself and what's happening to its populations right now. But we use this information in the context of species-specific traits. In other words, people sometimes ask, how is it possible that one set of criteria apply to all species? Well, it's not really one set of criteria because these criteria are interpreted in the context of species-specific information about the traits of that species. For instance, population trends are interpreted using the generation length of the species. In criterion B, we use information about the dispersal ability of the species and its habitat preferences, specifically how narrow the habitat preferences are. And in criterion C and D, we use information on the breeding system, life cycle of the species, and social structure in order to determine what's the best way to calculate the number of mature individuals. So there are species-specific traits that are used to interpret the symptoms from the populations, the data from the populations. And finally, there are information on threats. Threats information is used especially in two places. One is projecting future declines. Obviously, to make projections of future declines, we need to make some assumptions about future threats. And the other is location. In defining location, we use information about threats. But the important thing one important thing about the red list, and actually a strength of the red list system, is that even though it can use information about threats, it's not essential. In other words, you don't have to know why a species is declining to say that it is declining so fast, or the population size is so small or fragmented that it is a threatened species. Threat information, of course, helps, but it's not essential. And it's a strength because in many cases, we actually don't know why a species is declining. If we had to prove, that the threats we identify are the actual threats that causing the species to decline, it will be very difficult. It will be very difficult to justify. So that's a strength of the red list system. Now, with that in mind, here's another question that sometimes we get questions similar to this. It says data on a species indicates that it should be assessed as vulnerable. But this species is a top predator, and there are studies that indicate that in general, top predators are at higher risk of extinction. Because of that, should we list the species as endangered instead? What do you think? Does anyone want to say yes or no, or well, maybe it's difficult. Actually, I cannot even see the chat. Anyway, so I will continue with my answer, which is no, you should not. And the reason is that top predators have higher risk of extinction because of reasons such as they have low population densities and long generation lengths. But these factors are already included in the red list, right? And if data are sufficient and the criteria are applied correctly, then in this case, vulnerable would be the accurate category. So no adjustments are necessary. And as I said, if you make adjustments such as this, it would compromise the consistency and objectivity of the red list. Now, of course, any time that we have information about a species, that information is uncertain. And one of the difficulties we have is when data are sparse, how do we assess a species? And that's a very general problem. And the method that we use in the red list is first to acknowledge that all data are uncertain. There's no such thing as 100% certainty in science, and especially in conservation. So what we do, what we suggest is that instead of entering a single number, you enter an interval of values for each data. So there are uncertainties in occurrences of a species or its range area or population size or trends. All of these can be entered as a range of values rather than a single value. And that is the preferred way of dealing with uncertainty. So you can, for instance, as in this example, you can enter area of occupancy as a range of values, 900 to 1,000 square kilometers. You can also enter both a range of values and a best estimate. So you are saying that I'm pretty sure it's 700 square kilometers, but it could be plausibly between 500 and 1,000. You can even have your best estimate as a narrower range than the total plausible range. And you can enter, you can say, I'm pretty sure it's between 1,600 and 1,800 square kilometers, but plausibly it can be as low as 1,500 and as high as 2,300. So now uncertainty comes in all sorts of forms, of course. And one of the big issues is don't have much information about the species. Can you use information from other species? So here's the type of questions that we get sometimes: how to properly extrapolate data from one group of species to another. So in this case, it's kind of extreme, completely different taxonomic group, frogs to freshwater crabs, but they have similar habitat requirements. So if the only similarity between the species for which you have data and species for which you don't have data is habitat requirements, obviously you can only extrapolate things that have to do with habitat. So you can extrapolate decline in habitat quality, but you cannot extrapolate, for instance, area of occupancy or population size or anything else, right? You can only extrapolate habitat quality declines. But if you have more similarities, if there are two species in the same taxonomic group, perhaps in the same genus, they have similar body size, similar life history, similar habitat requirements, then you can extrapolate more. And these kind of issues are discussed in different sections of the guidelines, and I'll give an example when we talk about generation length later. Now, let me also say a few words about the last part of this question. The question ended by saying, without generating uncertainty. Well, there is no way. There is always uncertainty, and extrapolating from one taxon to another always creates more uncertainty. So there's always uncertainty. So don't be afraid of uncertainty. Instead, I say, use it wisely. That is to say, specify the uncertainty ranges for each parameter based on what you know. Now, here's a more difficult question, and the questions will get more and more difficult as we go on. How to assess a widespread species with few and small populations? Now, because it's a difficult question, I'll give a general answer applicable to many such cases and a more specific answer. So the general answer is a question like how to assess may suggest that you are asking which criteria to use. Don't decide on which criteria to use. First, enter all available data to SIS, and important to enter even those data that you don't think will contribute to the listing, because you never know. in combination with other data that you enter, that information may become important. Specify all data with uncertainties, and then use the SIS criteria calculator, which will give you at least an initial response of what the listing should be. And as I said, do not predetermine which criteria to apply. Don't say, okay, I'll use criteria B for the species. That's not in the spirit of the Red List. If you actually read the Red List criteria booklet, it doesn't start with a section on, in these cases, apply criterion A, in these cases, criterion B. No, it says criterion A, and then you apply criterion B, then C, then D. As long as you have data, you apply, and you stop only when one or more criteria are met for a given threat category, like endangered, right? So you don't decide on which criteria to apply before you do the assessment. Now, in this particular case of widespread species with few and small populations, the quantities that will probably come into play include things, of course, like area of occupancy, locations, number of locations, severe fragmentation, very restricted, which is criterion D2, and number of mature individuals. But it's also important in these cases to consider any evidence or information about declines. Was this species always did this species always have few and very small populations? If not, when did it get that way? Is it still declining? Are populations still being extirpated? So all of those go into the category of declines and reductions, and it's important to take those into account. Okay, so let's look at some questions. Next, I will talk about severely fragmented. So one question I have in the Q&A is, when area of occupancy and extent of occurrence include inferred and projected points, how do you calculate the number of locations? Do we count locations over the area or just in the known points? So of course, first, a reminder that locations is based on the threats that the species experiences. So locations can only be interpreted in the context of the threats. Now, when you are counting locations and mapping the threats in the different parts of the range, I think it's important to use the whole calculated range of the species. So yes, include areas that are based on inferred and projected points. So location is over areas, not over points, right? So if you have areas that you projected based on inferred points, then count the locations with respect to that total area. Now, of course, another reminder, more points does not necessarily mean more locations, because a large contiguous area or even discontinuous area can be affected by one threat, and it will count as a single location, regardless of how many occurrences of the species there are in those areas. If the whole area is the most plausible and the most severe threat is affecting all of those points, that will count as a single location. Any other questions?
Resit, we have only had two questions. One about how important it is to become to record threats for currently least concern taxa, and I've already answered that in the by Q&A, and I think someone from the Biopark team are answering a question about when extent of occurrence and area of occupancy include inferred and projected points. How do you calculate the number of locations?
Okay, so
how do we count locations over the area or just the known points? Yeah, that's the one that you've just been answering.
Yeah, that's the one I just answered. Okay. Great. So let's continue with severely fragmented, and that kind of relates to the last question, of course, which was widespread species, few and small populations. And when populations are few in a large area, that suggests that it's possible that they are it's a severely fragmented situation. So what is severely fragmented? Severely fragmented means that most individuals, this is the definition from the Red List criteria, most of the individuals are in small and relatively isolated populations. Now, I'll get to what small means and isolated means in a moment. But first, I want to mention that this is about population fragmentation, not habitat fragmentation, right? But in many cases, of course, we don't actually know the populations, but we can infer population fragmentation from habitat fragmentation. Nevertheless, it's always important to keep in mind that what we are trying to assess is population fragmentation. Okay, so we have interpreted small to mean not viable. In other words, increased probability of extirpation, and isolated to mean that if the population is extirpated, there will be a reduced probability of colonization. Now, I'll come back to the details of how these can be defined, but let me first talk about how it is actually let me first say that you should really see the guidelines, because there's an expanded section in the guidelines. We just expanded in version 15 that talks about this issue of what is small. Now, the IUCN criteria says that small populations may go extinct when it talks about severe fragmentation. So the way we interpret this is that the size of the population alone is the cause of increased risk of extinction. So it's not the decline. You don't consider whether it's declining or not declining. If the population size alone is sufficient to make this population not viable, then you consider that as a small population for the purposes of fragmentation. So a side note, a lot of people ask if the concept of minimum viable population is applicable. It is not applicable in this case. And if you want to know why, then we can discuss this later. But also, as an aside, this concept is not very useful for Red List purposes in general. Now, so what would we consider as small? It will depend on the species, but I would say that for most species, a population size in the low tens, in other words, 10, 20 individuals, 30 individuals, I would consider that too small. And for most species, again, a population size in the hundreds is probably large enough to consider that population to be not small, that it will be viable. It will not go extinct quickly just because of small population size. So somewhere between 50 and 100 is probably what the threshold is. Now, what type of evidence do you use to determine? So one type of evidence is that if a population has persisted for a long time with X number of individuals or in Y hectare of occupied area, then that's an indication that you can use those as thresholds that at which the population is considered not small, right? It's considered viable because it has persisted at that level for a long time. You can also look at population processes such as reproduction. If there's continued and sufficient recruitment or production of new offspring in a population of X mature individuals, then you can say that's probably an indication that X is a sufficient number for considering that population to be viable. So you have to think, it's a species-specific concept. You have to think in terms of what would be for this species a population size that is so small that regardless of any threats, it's likely that the population can go extinct quickly. The second is isolated. And that means, again, there's expanded section in the guidelines on this. I recommend that you read that section. But isolated means that it is too far from other subpopulations for recolonization to occur with a high likelihood. So if the population is extirpated, then it's likely that it will remain extirpated or locally extinct for a long time. That's what isolated means. And the type of evidence that you use for this is the dispersal distances of the species, dispersal ability of the species, or dispersal ability of similar species that use the same mode of motility and has the same body size, etc. So if the species is similar in morphology and mode of dispersal, then you can use data from other species to determine at what distance should you consider two subpopulations to be isolated because they are too far for recolonization to take effect with high probability. So those are how we define small and isolated. Now, how do we actually use it? So I made a few mock examples here to think about this. So here is one case. What we have is the map of the habitat of subpopulations. There are 5 subpopulations. And the question is whether this is severely fragmented or not. Now, looking only at the area of these habitat fragments, we cannot really say whether it is severely fragmented or not. We need to have a rough idea of what size or what population size or what area size, what fragment size we should consider to be too small to be viable. So let's put some numbers. Suppose we know that these are the number of individuals or the number of hectares in this case. Again, we cannot know because we don't know which number we should consider as a viable population size, right? Suppose that we looked at the evidence. We said that in populations with 40 individuals or so persist for a long time, and that we can easily consider any population that has 40 individuals or more to be viable, or it can be 40 hectares, whatever this unit is. Now, in that case, is this severely fragmented or not? In this case, it is not severely fragmented because if you count the number of individuals in the populations that are viable, it's 100 plus 40 versus not viable, it's 30 plus 15 plus 25. Most individuals are in populations that are not small, right? So since they are not small, it doesn't, it's not severely fragmented. Now, however, if we say, no, 40 is not viable for populations with only 40 individuals or area of 40 hectares, whatever this unit is, we see them extirpated. So we want at least 50 individuals to say that the population is viable. In that case, this taxon would be considered severely fragmented. Why? Because there's only one population that's above that threshold, and there are 100 individuals in it. All the other individuals are in other fragments, and if you add their numbers up, you end up with 110, which is more than 100, which means most individuals, so we go back to the definition, most individuals are in small and relatively isolated populations. Now, in this discussion, I assume that these are all isolated. Now, of course, if you have the same criteria of 50 plus, but you know that this is not isolated, this distance is not very large, and the species can easily go back and forth in between these two populations. Again, this will not be severely fragmented because the number of individuals that are in isolated and small populations then is only 30 plus 40 plus 25, which is less than half of the total number of individuals. So this will not be considered as if these are not isolated, this will not be considered as severely fragmented. So just a few final thoughts on the severely fragmented. Note that a taxon with a single population can be severely fragmented, but only under certain conditions. Only if that subpopulation is too small to be viable. Why? Because if you apply the definition at face value, right, it is a single subpopulation, 100% of the individuals are in that subpopulation. One subpopulation is by definition isolated because there is no other subpopulation nearby. So if that subpopulation is also too small to be viable, then it will be severely fragmented, even though there is a single subpopulation. Now, note that in this case, however, the taxon would likely meet criterion D as well at the higher threat category. So it's not a very common consideration that you would have, but still, by definition, a single subpopulation can be severely fragmented depending on the population size. Now, a taxon with two subpopulations can also be severely fragmented, but then there are two conditions. One, they must be isolated from each other, and second, both must be too small to be viable, right? But if the larger of the two is large enough to be considered viable, then most of the individuals will be in that larger population, so the taxon will not be severely fragmented. Now, sometimes the concept of severe fragmentation is confused with the concept of location, but these are actually, of course, very different concepts. They are independent of each other. A taxon may be severely fragmented, yet all the isolated subpopulations may be threatened by the same major factor, so there will be a single location, or each subpopulation may be threatened by a different factor. There will be many populations, or there may be two main threats, one threat threatening half of the populations, one threatening the other half, and then there will be two locations. So the number of locations is independent of whether the taxon is severely fragmented or not. The other difference, of course, is that severe fragmentation does not require an ongoing threat. As I mentioned in the beginning, location is one of the concepts in which the knowledge of threat is essential. You cannot use the concept of locations or the number of locations as a criterion if you don't know what the threats are. But severe fragmentation does not require that. It only requires information about, how fragmented the distribution of the population is. It doesn't matter how it got there. Regardless of how it got there, a taxon can be considered to be severely fragmented. Okay, so are there any questions on severe fragmentation before I go on to other topics? Okay, I see one question.
Hi, Resit. Yes, there's one question. Can you read it yourself, or?
No, but can you read it so that I rest a bit?
Sure, I can. So the question is, are there situations where historically secure populations of a species, maybe noted in the hundreds, have limited distribution, geographically distributed, but they might be considered vulnerable to extinction even though the numbers are robust? especially due to cumulative effects from anthropogenic stressors that didn't exist historically but are now imperiling that population?
Well, I mean, the straight answer is, of course, there are situations in which historically secure populations now have limited distribution, but whether they are considered vulnerable to extinction or not depends on which criteria the taxon fits. Now, if the limited distribution fits the thresholds of area of occupancy or extent of occurrence, and there is continuing decline and severe fragmentation, then it would fit criterion B. The other issue, especially from the second part of the question, especially due to cumulative effects of stressors that didn't exist historically and are impairing the population now, that information can be used to calculate the number of locations. And again, number of locations can contribute to the criterion B assessment. The other option would be that the species can be assessed as vulnerable under criterion D2, again, if it fits the definition. But just the information that the species is geographically more limited than in the past is not sufficient. You have to have it has to fit some of the criteria. Now, if the numbers are robust, as the question says, which means that there is no continuing decline, but if the population range area is very small, so it fits area of occupancy or extent of occurrence, then even if there is no continuing decline, it may be there may be severe fragmentation, there may be fluctuations, there may be number of locations, few number of locations. So the taxons can still fit a threatened category even if there is no continuing decline.
Thank you, Resit. We have another question, I think. So the question of isolated populations and fragmentation is also linked to the genetic structure of these populations, specifically on plants that may be autogamous. In other words, the diversity is between populations. That means what is more important is many different populations of a few individuals and not having one large population itself. Or allogamous, which meaning that it's more important to have a few populations of diverse individuals. I'm afraid I don't understand what that is saying.
Okay. So the genetic structure is, of course, a symptom of in some cases, population reduction or population fragmentation. But genetic structure itself is not used in IUCN criteria because of multiple reasons. One is that in many cases, we actually don't have, for most taxa, we don't have genetic information. The other thing is that the relationship between genetic structure and extinction risk is not established as one single function for all species, so for all taxonomic groups. So it's difficult to make a generalization. And the other reason is that in many cases, the genetic changes in genetic structure is a lag symptom. In other words, you see the population fragmentation much earlier than you see its reflection in the genetic structure of the species. So, it's an earlier warning in many, not always, of course. There are always exceptions to these things, but it is an earlier warning system to base the assessment on the population structuring rather than the genetic structuring, but for the obvious reason that extinction, as we are concerned in the Red List, is defined in terms of demography, right? The last individual going extinct, the population size declining to zero. So the population level symptoms are really much more direct assessments of that risk. But anyway, this is a bit beyond the scope of this. I have other thoughts, and there's a lot have been written on this as well that we can discuss separately. But the main answer is that if you have enough data to actually show effects of fragmentation being reflected in genetics, you probably have enough data to show that the species has fragmented populations and assess it based on that. Is the general answer I would give. Any other questions?
Thanks, Resit. No more questions at the moment.
Okay. So let's move on to reductions, and I'll start with a difficult question, another difficult question, and it says, if recent field surveys did not find a species in the few localities where it was previously recorded, is this enough to determine a population reduction? It's a difficult question because you need to consider the difference between three types of declines. I'll talk about this in an upcoming slide in just a couple of minutes. But it's important in these kind of cases to know other potential habitat areas that were surveyed. And by surveyed, I don't mean just planned surveys, but coincidental surveys. People going and people would have noticed the species there if it existed because they were looking for something else, and they would have reported it. That sort of incidental surveying. Dispersal ability of the species, how cryptic it is, how easy it is to see the species, and survey effort. All of these are important in trying to determine if there is population reduction. Depending on these information, possibilities include suspected reduction. Note that a reduction under criterion A can be suspected, and that's a lower level of evidence that's required than inferred reductions. But another possibility is inferred continuing decline, which is different, as I'll come to in the next slide, or in a few slides. There are important differences between reduction and continuing decline. But I would say another important thing to consider in these cases is the possibility of extinction. So a species can be assessed as critically endangered, possibly extinct, if field surveys did not find the species in a while. So if the species has not been recorded in several years, it can be listed as possibly extinct, depending again on the survey effort and how cryptic the species is. And there are now detailed guidelines about this in terms of how do we know, how exhaustive the surveys are, how do we quantify it, and how do we use all of this information to decide whether the species should be listed as possibly extinct. But I would say that if it doesn't fit that, then in most cases these failed surveys can be used as evidence for suspected declines. Now, another related question this is another difficult question. Wild populations of a plant species in commercial use may be getting smaller. There is fairly reliable evidence, but anecdotal evidence, such as increasingly longer time needed to collect a given amount of the species, or species disappearing from localities where it used to be abundant in the past. However, there are no focused surveys. Should this species be assessed as data deficient? I would say that it seems like there is enough information that data deficient would not be necessary. I would say, first of all, consider the difference between the three types of declines that I'll talk about in a minute. But I would say, in general, this sort of case probably will not be data deficient, because criterion A2 can be used with suspected reduction. And in the new version of the guidelines, there are more examples about what constitutes suspected as opposed to inferred types of evidence. And also, continuing decline can be inferred from things such as increasing pressure on the species from commercial use, disappearing from known locations. All of these are information that can be used to infer or suspect declines. The other thing is that if there is any trade information, population sizes or reduction in population sizes can be approximately estimated, and even a wide range of uncertainty may allow assessment under criterion A or under criterion C1. People who do assessment of fisheries, for instance, do this all the time. They go to fish markets and record the number of different species that are seen, and then the trend over time, combined with the information about effort, which is how many the size of the fishing fleet, etc., gives really important information, clues about population trends. Now, here's another complicated slide to talk about the three types of declines. First, there is the continuing decline concept and reduction. And these are different because reduction, which is used under criterion A, does not have to continue. It can be a ceased reduction. You may even have a population that is currently increasing, but overall it has declined in the last 3 generations, right? So reduction can be used, criterion A can be used even with a currently increasing population. Whereas continuing decline is recent, current, or projected future decline that is liable to continue unless remedial measures are taken. Now, continuing decline is continuing, obviously, that's what it says, but actually future projected decline is considered to be continuing decline as well. Now, it's very important that there are 2 different versions of continuing decline in the criteria. One is called estimated continuing decline and used only under criterion C1, and other continuing decline is used in criteria B or C, B or C2. The continuing decline at any rate can be inferred, and the units are basically whether there is decline or there is no decline. It's true, false. There is continuing decline, there is no continuing decline. Now, it's true, false, but as with any other parameter, this can also be uncertain. So if you think true is 1 and false is 0, you can actually enter any number in between those to indicate your uncertainty about whether there is continuing decline or not. Estimated continuing decline, however, it's not a true-false thing, it's a percentage. And the thresholds are 10%, 20%, or 25% over 1, 2, or 3 generations, or 3, 5, and 10 years, respectively, whichever one is longer. So C1 it's the same kind of continuing decline concept, but it is applied quite differently because you need an amount of decline. You have to apply it over a specified time period, and it has to be observed, estimated, or projected. The other differences between these three types of declines includes the additional conditions that are necessary for those declines or reductions to trigger a category of threat, right? So for criterion A, there are no additional conditions. If a population is declining by, let's say, 50% over 3 generations, then it's endangered regardless of any other attribute of the population. Even if it is a large population, even if it is currently increasing, if it has declined by 50% over the last 3 generations, it's an endangered species, right? Whereas for continuing decline, there are other conditions. There are, for estimated continuing decline, the main other condition is number of mature individuals under criterion C1. The population must be smallish and declining. And under B and C2, there are several other additional conditions, including range area, number of locations, fragmentation, fluctuation, mature individuals, etc. So there are many other conditions. Now, reduction and decline are complex topics, and they are really important for identifying threatened species. And these are covered in several different sections of the Red List guidelines. And these sections are updated quite frequently. So I strongly recommend that you consult those sections. I think in sometimes these are not applied as much as they could be applied. So some people think that criterion A, for instance, could be applied more frequently. See if the data that you have can support reduction or decline criteria. Now, for both estimated continuing decline and reduction, the decline or reduction is interpreted for the particular species in the context of its generation length. Generation length measures the turnover rate of the species population, and it's important because the declines or reductions in calendar years are not meaningful in an ecological context. To make them meaningful for the species, we have to put them in the context of that species' life history. So that's why we use generation length, which is the average age of the current cohort, age of parents of the current cohort, and I'll come back to different definitions of generation length. Important points to remember. The generation length is greater than age of first reproduction or age of maturity, unless the species breeds only once, right? So ignoring the species that breed only once, if a species breeds only once, its time of breeding and generation length are the same thing. If a species breeds more than once, potentially, then generation length is always greater than age of first reproduction. But it's also less than the reproductive lifespan. So it's between those two numbers. And it reflects the turnover rate of the breeding individuals in the population. And the way it's used in the Red List is it scales time-based measurements to account for the different rates at which taxa reproduce and survive. And there are many topics discussed about this in the guidelines. One is, for instance, to always use the natural generation length, not generation length modified by a threatening process. Particularly under exploitation, generation length of species declines. We want to use the natural generation length of the species. Okay. Now, how do we actually estimate? Now, before getting into the practical methods of estimating, let me first discuss the conceptually what are the different definitions of generation length. So the first one is average age of parents of the current cohort. So basically, you go to the population and you look at all the individuals that are newborns this year. No, they are born this year. If you know their parents, you say, okay, what's the age of the parents of the current cohort? You make a histogram of the age of the parents, and the youngest parent would be, a young individual, and there is the oldest parent, and the median of this, or the average of this distribution, would be one definition of the generation length of the species. Now, you may be asking how it's possible to, know the average age of the parents. How is it possible to age the parents of each newborn? But actually, for some species, it's quite simple. So, for instance, you are looking at a plant, right? So all you need to do is look at all the mature individuals that produce seeds, right? And then if you know the age of the individual that produced the seed, then you know the age of the parent, and then you average those parents' ages, then you get the generation length. Now you may want to weigh it by the number of seeds. If there's a large variation, some individuals produce more seeds, because each seed can be considered actually as one individual of the current cohort. So if one parent has more than one offspring, for each of them you enter the age of that parent. Right? So that's one definition. Now, this is not applicable to all species, but it's just conceptually, that's what it means. Now, the second definition is mean age at which a cohort of newborns produce offspring. What does this mean? It means that you mark or tag or band all individuals that are born this year, and then you follow them throughout their life, and then say, when is the first individual of that cohort started breeding? And then when is the last individual of that cohort bred? And the average of those is the generation length, right? So that's another conceptually what generation length means. And the third one is very similar, actually, age at which 50% of total reproductive output is reached. So imagine you are following a typical individual throughout its lifetime. Reproduction starts at some point, then a young individual doesn't have that many babies, the reproduction peaks at some point, and then at some point there is senescence and the individual stops breeding, and then the 50% of the reproduction occurs at a point in time, which is another definition of the generation length. Okay, so those are the three definitions. I should also say that technically, actually, those are three different things, and when you have a lot of data on a species, you may end up with three different numbers, which is okay. You can just use any one of them or take their average, this happens very rarely, by the way. You need a lot of data to be able to estimate all three generation length definitions. But here is some examples. So what do we do when we have much less data? Suppose you only know the first and last ages of breeding, right? You know the age of first reproduction and the length of the reproductive period, the last breeding age. There's a formula for this in the guidelines. I don't know why it's going forward. You multiply the length of the reproductive period with a number that we call Z and add the age of first reproduction, right? So Z is a number between 0 and 1. Usually it's less than 0.5. And you can use this value from similar species. So for mammals, for instance, there is a paper that's referred to in the guidelines that calculated an average for all mammals about 0.29. And there's another paper for birds. It calculated the average based on age of first reproduction to be between 0.14 and 0.32. So it can be estimated from related species with more information. So here's an example. First reproduction is at 3 years of age. Last reproduction is at 10 years of age. So length of reproductive period is 7 years, right? And let's say Z is estimated to be 0.3 based on species in the same class. So generation length would be the length of reproductive period, which is 7, multiplied by 0.3, which will be 2.1, plus age of first reproduction. Hey, this is wrong. Should be 3. Sorry, I made a mistake. Anyway, should be 5.1. It should be 5 plus this number. I should check my math. This is so embarrassing. I can also say, as I make this joke with my students, I was just trying to see if you are paying attention. But I won't say that. I actually made a mistake. Okay, here's another example. If you only know the first age of breeding and you know average adult mortality, and again, there's a formula for this in the guidelines, and you add age of first reproduction, to 1 over adult mortality. And here's an example, age of first reproduction at 2 years, average adult survival is 60%, so mortality is 40%. 1 over mortality is 1 over 0.4, which is 2.5, plus age of first reproduction, so the generation length is 4.5 years. Now, this formula is useful if adult mortality after the age of first reproduction is pretty well known, and if you have reason to believe that mortality and fecundity do not change with age of first reproduction. In other words, there's no senescence. Because if there is senescence, you should also consider using the age of last breeding and as part of the information. Okay, so here's a question about this. I have the following information for my species. Age of first breeding is 3 years, age of last breeding is 15 years, adult mortality is 0.66, and I think Z is between 0.3 and 0.4. Now, because we know both mortality and age of last breeding, we can use both of the formulas that I mentioned, right? So if you use one of the formulas, you get 1 over mortality, 1 over 0.66 plus age of first breeding gives 4.5 years. If you use the other formula with Z, you can use it with Z is 0.3 or 0.4, but whatever you use, it is a much larger number, 7 to 8 years, right? So is it 4 to 5 years or 7 to 8 years? Which one is correct? Does anyone have an answer? I guess you are all muted. Okay. Well, so actually, you cannot say which one is correct, but let me explain it. It's a long answer. So it says adult mortality is 66%, right? So that means survival rate is 34% per year. In other words, every year, only 34% of adults go to the next age, right? Now, we don't know what happens to the juveniles, but usually juveniles have even lower survival than adults. But let's assume that juveniles have the same survival rate as adults. So if an individual on average has 34% chance of surviving to the next year throughout its lifetime, what proportion of individuals will reach age 15? right? You can calculate that. And that calculation is 0.34 multiplied 15 times by itself. And that number is 1 times 10 to the minus 7, which is about 1 in 10 million. Okay, so what does this mean? It means that these 3 pieces of information that we have here are not consistent with each other. There's something wrong, because you cannot possibly know for most threatened species, you cannot possibly observe a 15-year-old individual if annual survival is only 34%. You would need to age 10 million individuals in order to get to that one 15-year-old individual. You need to be extremely, extremely lucky. It doesn't mean it's not possible. It just means that it's very, very unlikely. So more likely is that there is some inconsistency. So either the age of last breeding is overestimated. So this is, for instance, it may be based on individuals in captivity, or there may be a mistake in estimation, or annual mortality may be overestimated. It's possible that mortality is much higher, much lower, and survival is much higher, and we underestimated survival because the data are wrong, or because the data did not take into account, what proportion of banded individuals travel outside the study area, that sort of. There are lots of reasons why that might be the case. But the important thing is that we need to carefully check the original data, that one or the other of these 2 pieces of information is likely wrong, and we need to decide which one we trust more, and then we decide which number to use, either 4 to 5 years or 7 to 8 years, based on that information. Okay. Here's a more difficult question. Well, that was difficult too, but this is also a difficult question. How to calculate generation length for a species with a persistent soil seed bank if seed viability and residence times in the soil banks are unknown? So residence time is, I interpret this as time to germination. That is the time from the time that the seed is in the soil to the time that it germinates, calculated only over the seeds that do germinate eventually, not excluding the seeds that never germinate. Now, in general, how do we try to assess the generation length of a species, of a plant? So if it is possible to age mature plants, we can take a random sample of all seed-producing plants and determine their ages and calculate the average. Right? That's the example I gave earlier. We know which individual is producing seeds. We age all those trees and take the average, and that is the average age of mature trees, right? But this is likely to be that age that we calculate is years since germination, not years since the seed was deposited, right? So we are missing that part from seed to germination. So it may actually underestimate actual age, which is missing the years since seed. And this is difficult if we don't know seed viability and residence times. However, we can use information from related species and add the median residence time of related species in the soil. And this should not be the maximum residence time. In other words, it's not like at least some seeds survive in the soil for 10 years. That's not the number we are looking at. We are looking at the median. If you deposit 100 seeds and 50 of them will eventually germinate, when does the 25th of them germinate? What's the median germination time of the seeds that actually survive, right? So that's the sort of thing that we are looking at. And that number is likely to be much smaller than the maximum residence time in the soil, right? So it's likely to be a very much smaller number, and we can add that to the number that we calculate from the first step. Now, this is going to be a crude approximation, but it is still better than not using generation length at all. Even if you have to just say, okay, the average age of mature trees is, let's say, 15 years, and I don't know anything about residence in the soil, so I'll just assume conservatively it's only 1 year, right? So instead of 15, I use 16. That's okay. It's still better than not using generation length, right? Because if you don't use generation length, you cannot use criterion A or criterion C1. You would be throwing out a lot of information that you could otherwise use. So it's better to approximate even crudely than not use generation length at all. Okay, any questions? So we actually don't have that much time left. So maybe just not just about generation length, but in general, if there are any questions. If not, I can talk about climate change. But
sorry, Resit, there are no questions at the moment that have been unanswered. So I think you can carry on for another 10 minutes or so.
Okay, well, 10 minutes is obviously not enough to cover climate change. It's a very complex topic, but I will just briefly mention a few things that we get questions about frequently. First, there's a long section of the guidelines that specifically focuses on climate change. So if you have any reason to believe that climate change may be affecting the species that you are assessing, I strongly recommend that you consult that section. And that section is based on this step-by-step process in which you consider increasingly more complicated types of information to determine what the how to assess the species. So first, as I mentioned at the beginning, the Red List criteria are symptom-based. So they are based on what is happening to the populations, and implication is that you don't have to know that the species is threatened by climate change. The symptoms of the species may still correctly predict what the threat category of the species will be. And it allows, incorporating indirect effects. And now we did a simulation study of this. I won't go into the details, but what we determined is that the Red List criteria, even if you don't explicitly model projected climate change effects, Red List criteria gives sufficient warning time if conservation action is taken when the species is listed at the lowest threat level, vulnerable, and if data are available to use at least two criteria, like A and B or B and D, at least two criteria, then there is sufficient warning time. So because of that, the first option is to make Red List assessments as before without explicitly modeling climate change, which would still, so don't think that because you're not explicitly modeling climate change, there's no hope that you'll be able to correctly assess the species. No, you may still be doing pretty good job, pretty good approximation. So, but of course it may not be sufficient for some species, but better than anything else, right? It's still better. As I mentioned, we have validated this approach, and the Red List criteria is actually the only climate change vulnerability assessment system that has been quantitatively tested and validated to assess species correctly. So that's important. However, you have to use as many criteria as possible, follow the guidelines, use appropriate time windows. That's another issue that's discussed in this climate change section. what time frame we use. And keep in mind that unless you explicitly model changing climate, you may still be underestimating extinction risk due to climate change. So option 2 is to consider the mechanisms of climate change and do the red listing as before, but systematically think about if climate change is affecting the species, how would it actually happen? Now, what would happen? It would species stop reproducing in the southern parts of the range? And if it does, how fast would it decline? Now, you can make a lot of these kind of projections based on life history of the species and known climate exposure in the region, right? And the guidelines also give a lot of information about how to define key red list parameters in the context of climate change. In particular, locations can be defined based on the effects of climate change. And even just knowing that and using location in that way can increase the threat status of a species. Now, the third option is more complicated, is to develop climate-based species distribution models. So these are basically statistical models that are used to project where we are likely to find the species in the future as the climate changes. And they are used to predict future potential habitat, which in turn can be used to infer reduction or continuing decline based on climate change. Now, how that is done, I cannot tell you in 5 minutes, but there is detailed guidance about this in the Red List guidelines. It requires data on point locations of where you currently observe the species, data on climate layers, which is available globally actually, and in some cases land use as well if you want to use it as a mask. And it also requires modeling expertise, at least somewhat. But we are trying to change this. There are some initiatives to develop training materials and easy-to-use online tools that will allow Red List assessors to incorporate these types of projections into assessments more easily. I cannot say much more about it. We have been thinking about it for a long time. There are a lot of technical issues to resolve to do that, to develop a general enough tool, but that's what we are hoping to accomplish. So I think I'll stop here. There are other options, but they are even more complicated, so I won't go through these. But basically, you can continue doing Red List assessments as before, or consider the mechanisms of climate change as defined in the guidelines, or develop these species distribution models. So I will now stop sharing my screen, and yeah, Caroline, go ahead.
Thank you, Resit. Thank you very much for that. That is actually all we've really got time for in this webinar. And thanks very much, Resit, for giving us some insight into the Red List criteria and for taking the time to answer some of the more difficult questions that people have. Very much appreciated you taking the time to do this. Thank you to Albuquerque Biopark for help making these webinars actually possible. We've been thinking about these for a long time, and it's just thanks to Albuquerque Biopark that we're making them a reality now. Particular thanks to Clay Meredith for his practical solutions to what I thought was a very difficult and challenging task, reaching out to such a large and valuable network of people. So thank you, Clay. And of course, thanks to Anna Walker and Tim Lyons for helping to field the questions that were coming in the Q&A section as well. And of course, thanks to all of you, the SSC network, for joining us today and for asking those important burning questions. We need your feedback. We need you to push us on on getting the right guidance and support out there for you. It's not always obvious to us. The recording of this webinar will be shared with all of you after the webinar, probably in the next week or so. And we will try to make this recording available online, probably via the Red List website. I'm not sure when that will happen, but that's the plan. I think we managed to answer everyone's questions, so that's a good thing. We will repeat this webinar next week on Thursday, the 26th of April, but 12 hours later than today's time slot, because we want to encourage other people from other regions to join us. So after next week, we will have the next IUCN Red List webinar in August. We'll announce the dates soon, but that webinar will focus on how to prepare distribution maps for supporting information for a Red List assessment. So we'll circulate an announcement on that very soon. And thanks again for joining us, depending on where you are at the moment. Have a good morning or a good afternoon or a good evening or a good night. Thank you very much.